myself SK Sahil Akhtar. So today I am going to present you my project, or you can say my experiment, which is the experiment number 3 for digital communication. So today we are dividing into digital communication and signal processing by looking at the experiment 3, as I have said you earlier. So which will be about sampling, aliasing, and sync reconstruction using Python and Google Colab. Okay. So just 1 second. Mouse is disturbing me. So, uh, 1 second. Okay, no problem. So, this is the project, or you can say this is the experiment which I have uh, run on the Google Colab, and this is on your and this is the format uploaded on the GitHub. You just go to my profile, and after that, when you go to my repositories, then when you click on the digital communication profile, then after that you can see here one folder which is named as IPYNV. When you click on it, then you can see here the code it is now processing because it is directly connected from the Google Colab. So here you can see this. The import MPI, which is the code. Okay, so later I will explain you this code. Here is the code, and here is its output. Just 1 second, my mouse is creating a problem. So okay, so you can see here. Okay, then after that, here is the code actual in the Google Colab, and here is the output. Here is the output. You can see. Okay, okay. So let me tell you about this. So now in this video, we are going to verify the Nyquist channel sampling theorem hands-on. We will simulate continuous time signals here, sample them at different rates, reconstruct them using Sinc interpolation, and observe what happens in both the time domain and frequency domain on Aliasing. Okay. So all code and plots shown in this video are available on my GitHub repository, as I have told you. And I try to give a link of my GitHub in my YouTube description. If not possible, then I will sure add them to the comments. Okay. Okay. So now let's talk about the theoretical setup and math validation. So let's define our test signal. Okay, we are working with a continuous time signal. We are working with a continuous time two-tone sinusoidal signal given by, you can say that x of t equal to sine of 2 by f1 t plus zero point 0.5 sine 2 by f2 t. Okay, so here are two different frequencies. So let us suppose we choose frequency number one, which is which is, you can say, 10 hertz, and the frequency number two, which is 50 hertz. Okay, since the highest frequency component, that is f max, that is 50 hertz here, the theoretical Nyquist rate, which will be two times of f max, is 100 hertz. Okay, so here is the Nyquist rate. You can see here in the code. That is here the commented as added. That is the 100 hertz. Okay, to see the full physical picture, we test three distinct sampling frequencies. Okay, so first we can see oversampling at 300 hertz, so which is where fs is greater than two times of f max. Okay, so critical sampling at 100 hertz, you can say, where fs equal to two times of f max. Under sampling at 60 hertz, so where fs is less than two times of f max. Okay, so these things are written in my copy. I am not able to show you right now those things. So now before running any code, let's perform the mandatory theoretical validation for the undersampled case at 60 hertz. Okay, the folding frequency limit is half of fs. Just 1 second. Okay, the folding frequency limit is a half of fs, which is 30 hertz. The 10 hertz tone below, or the 10 hertz tone is below 30 hertz, so it remains completely unharmed. However, the 50 hertz tone exceeds 30 hertz. See here, the 50. Oh, sorry. the 50 Hz tone exceeds the 30 Hz, it falls back into the baseband according to the aliasing equation. Okay. So here the F alias is equal to a mod of F2 minus K times of Fs equal to 50 minus 1 into 60. That you can say that is 10 Hz. This means our 50 Hz component will fold right into 10 Hz, correcting our original signal shape. Okay. So now let's go through the code. Okay. Okay. So now let's move to the Google Colab tab as it is already moved. So I don't need to move that to here. So here we will see how we have implemented it using the Python lab. As you can see here, it is written that your PYP dot. Okay, just 1 second. Just 1 second. So first notice how we set up our time axis to simulate a continuous analog reference signal. We generate a very high resolution grid that is T fine sample at 2000 Hertz. As you can see. Okay, this keeps our physical sampling rates strictly. Just 1 second. Sorry, some unavoidable circumstances came here. So, okay, so what I was here, that I was aware that we generate a very high resolution grid that is T fine sample at 2000 Hertz. This keeps our physical sampling rate strictly separated from our plotting resolution. Okay, so next we should define our Sinc interpolation function. Okay, so here uh, you can see here that the Sinc interpolation. I must not disturb the equation. Okay, so here you can see that is Ts that is equal to 1 by frequency 1 by Fs, and here in the Sinc matrix is written. I must not go very deep into that. Well, so according to Whittaker channel, interpolation theory, perfect signal reconstruction is achieved by convolving discrete samples with a shifted sinc function. We construct a 2D sync matrix and perform a matrix dot samples without discrete sample values. That is your X samples that you can see here. Okay, X samples. And then finally, we use matplotlib to generate 4 columns for each case reference and discrete sample sync reconstructed waveform, absolute error and magnetic spectrum called via calculated via FFT. Okay, so now analyzing visual results and observation. Okay, so let us now go to the graph. Here is the code actually the given. Here is the actual code given. I actually cannot zoom it very much. It is not possible here with it. So here in GitHub, the code is written very much clearly. If you want, then you can observe or see those from here. Here, the only problem is that the graphs are shown in a little size, but here the graphs are shown in a very big size. But I am unable to zoom it on. Okay, just 1 second. It is a little bit of problematic to use. Okay, so now let us analyze the generated plots row by row sticking. Okay, just 1 second. I cannot, I am not able to adjust this properly here. So let us see from here. Wait, just 1 second. So here you can see, so here you can see the row one. That is your Fs is 300 Hz here. Now look at the column two. Now look at the column two. The green reconstructed signal overlays the black dashed original signal perfectly. You can see what is here. Okay. The absolute reconstruction error in column 3, 1 second, in column 3 is virtually zero. And looking at the spectrum in column 4, both the 10 Hz and 50 Hz peaks match the original continuous spectrum without any distortion. Okay, so here in our row 2, you can see that exactly at the Nyquist rate, sync interpolation still manages to recover the continuous signal without losing frequency information, as demonstrated by the dual peaks in the magnitude spectrum. Okay, then then you can see in our row 3, which is the case of undersampling, that is fs for 60 hertz. Here is where the aliasing phenomenon becomes clearly visible. Look at the reconstructed waveform in your column. Here, in column 2, it looks completely different from our original signal. It looks completely different from our original signal. So, looking at the magnitude spectrum in column 4, the original 50 hertz spike has completely vanished. Instead, it has folded directly into your 10 hertz. Okay, that is this one. Sorry, which one was that? Then this one. Okay, which is the original 50 hertz spike has completely vanished. Instead, it has folded directly into your 10 hertz, combining with the fundamental tone exactly as we calculated when. So now let us come on to the conclusion. Okay, so to summarize our findings, the Nyquist-Shannon sampling theorem holds true. Sampling at your Fs that is greater than equal to 2 times of Fmax is mandatory for lossless reconstruction using Sinc interpolation. Okay. And undersampling leads to irreversibly aliased frequencies that severely corrupt both the time domain envelope and the spectral distribution. Okay. If you, and here, if you find this video helpful, make sure you hit the like button and subscribe to the channel for more digital communication and signal processing experiments. Okay. So in future, I also upload these types of videos. Please subscribe me, and you can find direct link of the GitHub in the description. Okay. So thank you very much.